Assalamualaikum warahmatullahi wabarakatuh, and hi to everyone. So today we will continue with chapter number 2. So on the topic of transformer. Okay, right. So this is some of the learning outcomes whereby at the end of this topic, student must be able to know the fundamental concepts of types and construction of transformer. So this is the very basic principle of types of transformer and its construction, especially the physical construction, so that made up transformer. Secondly, to understand ideal transformer, theory of operation of real single phase transformer and its equivalent circuits. So we try to figure out how the ideal transformer when we convert into the equivalent circuits, and for there you must be able to understand the theory of the operation and how the analysis should be carried out. Before we jump over to point number 3, where you must be able to analyze equivalent circuit and transformers voltage regulation, the VR over here, and its efficiency. Okay. Then the last but not least is to be familiar with three-phase transformer and its characteristics. So we will look into, I would say, quite detail when we come to the three-phase transformer. So why transformers are important to modern life? It is because transformer, okay, is one of the most useful electrical device. It is able to first raise or lower the voltage or current in an AC circuit. So this is one of the feature or the key advantage why transformer is very important so nowadays. So the ability of to raise or to lower the voltage, even though the current in AC circuit, and then isolate circuits from one to another, because we can see from its construction over here. Oops, here you can see that the part is divided into two leg of core, for example, and being wounded before we may inject certain level amount of current, and it's being the voltage is being induced according to the number of turns, and finally generate or energize the bulb. Okay, so it may in other words, to isolate between here, okay, circuit to that. So we have the coming as well as this is the outgoing, okay, the load where the load is placed. So to change the impedance of the load as seen by the source does enable load matching, which result in maximum power transfer. So we will see in the content of the chapter how we able to change the impedance, especially the load. So seen by the source, we can actually transfer or move over the loads in the equivalent circuit into the source part or source side, okay, which enable the load matching that giving us the maximum power transfer. So next, transmit electrical energy over great distance. Okay, so this is what DC cannot do. So we can actually do by having the transformer element or equipments in our transmission line, the AC transmission line. So the ability of the transformer again to transmit the electrical energy, and to distribute it to end users. So again, transformer give to AC a feature lacking in DC power system. For example, efficiently change AC voltage from small amplitude to large amplitude, and the other way around. And where in general, the higher the voltage, the more insulation. So this is quite common. So when the level of voltage is higher, and then so it's require higher or more insulation as well as the switching costs, but less current use. So when we come to efficiency, so it's obviously sees that I square R loss is lower. Okay, and yes, efficiency is much better. Okay, some of the principles of transformer. So principal purpose of a transformer is to convert AC power to at one level voltage to AC power of the same frequency at another voltage level. So this is the interesting part of the transformer. So we do have the same frequency, theoretical frequency, for example, whereby at the same time the transformer itself is able to convert AC voltage at one level to another, whether step up transformer or step down transformer. So some application of transformer are so voltage sampling, current sampling, as well as the impedance transformations. Types and construction of transformers. So transformers classify into two types of cores, namely core form, whereby each winding may be evenly split and wound on both legs of the rectangular core. Okay, so we can see here, so the core form type where do have, let me change the color. So we do have both leg, for example, here. Okay, we have two legs over here being wounded, okay, by a collar. Here, we can have three legs core and three sets of winding. Okay, so this is for single phase, and here is for three phase. Okay, and the second one is shell form. So the two windings are usually wound over the same leg of the magnetic core here. Okay, so we have a single phase. All right, so we have the middle one which is being wounded. Okay. And similarly here we have a three phase and we have three legs as well. 1, 2, and 3. So you can see the configuration of the winding is dissimilar or different compared to the core type. Okay, here. And then some of the the real example of core type transformer. So this is quite common, I believe. We have seen this everywhere and quite some time. The core type transformer and then the shell type transformer. So we do have a big or huge set of transformer for example here, where we do implement or we do install at the uh, power plant, sorry, and also station. Okay, and types and construction of transformer. So potential transformer as well as the current transformer. And for potential transformer, sampling a high voltage and produce a low secondary voltage proportionally, and it is actually to handle very small current. And then for current transformer, it provides much smaller secondary current than but directly proportional to its primary current. So this is the interesting part of the current transformer or CCT. So some of the real example we can see outside there, the potential transformer over here, okay, the transmission line, for example, okay, here also we have, and then here the current transformer, you can see, okay, from the shape over here, okay, this is actually the terminal. So we do have the metering current transformer up here as well as the voltage transformer. But somehow the current transformer also be used in order to measure the level of current. Okay. So now we come to the ideal transformer. So some of the assumption we can make in order to make our or to create an ideal transformer. So what some of the consideration we should take into account. So first, it is infinitely easy to set up a magnetic flux in the core. So we can say that it is the magnetic flux, okay, can be actually induced or set up in the core very easily. Okay, so or alternatively, we could see that the core permeability is infinite, okay, and the reactance of the core is zero. Right. So the lesser or the lower the value of reluctance, meaning the higher the permeability. Okay, the permeability over here to produce or to generate magnetic flux. So the magnetizing current required is zero. So there is since reactance core is zero, and then the magnetizing current required one is also zero. So the no magnetic flux leaks out between the two windings. So we can say that there is no any leakage in terms of flux, and to say that all the flux is actually links all the turns. Okay, so it make or they link up between one turn to another without any leakage. Everything is perfect or flawless. So the winding resistance is also zero. Okay, so we have seen that the reluctance inside the core is zero. So the winding resistance, we come to the winding resistance is also considered zero, and there is no at all the hysteresis or the eddy current power loss in the core. Okay, everything seems so ideal. All right. And then the current, voltage, and flux in an unloaded ideal transformer. So remember, so our core over here, so we have seen this quite sometime in topic number 1. So where we have our rectangular core over here, and at this both leg number 1 and leg number 2, we have our respective winding. All right, so with the VP, the primary voltage, as well as the induced voltage at the primary side. So we have the primary current and the number of turn still at the primary side. So once we move on to the leg number 2, again we do have our coil over here, our winding over here with NS, the number of turn, and also the induced voltage at the secondary side, the current or IS, as well as the VS. So the blue dotted line over here represents the flux, okay, the M flux and the mutual flux. So EP, the induced voltage at primary, we have this relation where NP multiplied by flux M of omega over square root 2. So what is omega? This is actually nothing but angular velocity. We have d theta over dt. All right. So what about ES? So no difference. Instead, just except for the notation, so it denoted as S, which is standing for secondary. Again, still in the ideal transformer, what happened to turn ratio A? So what can we define by this parameter? So we have A equal to NP over NS, or this is VP over VS, or IS over P. So P stands for primary, S stands for secondary. Okay. So you can actually calculate A by using number of turn. So you can also using the value of volt as well as the current or the ampere. And power P in equal to Vp Ip cos theta P. So this is for reactive power Q, and this is for output power. So we have output power where this is actually supplied to load, all right, as well as the Q out, okay, and also the apparent power, okay. So Vp Ip equal to Vs ISS S out. Okay, and then here, since Vp over Vs, so we have seen here this relationship earlier. So then we rearrange. So we can say that VPIP equal to VSIS, thus VPIP cos theta equal to VSIS cos theta. So the output power of an ideal. Okay, this is the key word. So remember, we are still analyzing under the subtopic of ideal transformer. So the output is equal to its input power. So this is proven in our analysis here. Alright. Oops. Okay. And then transferring impedance through a transformer or load matching. So with transformer, it is possible to match the magnitude, okay, of a load and impedance to a source impedance simply by picking the proper turns ratio. So here, this is how the equivalent circuit looks like. So we have again the VAC, okay, we have IPVS all here. So this is the winding. So this is the winding, particularly for primary part as well as the secondary part. So in between we have the turn ratio. Okay. So here this is, for example, NP over NS. Alright. Okay, then what happened? According to this statement, okay, we can actually match the magnitude of load impedance to a source. We could say that over here the load can be transferred from here, okay, by crossing the transformer, especially the turn ratio A, okay. So this is how we analyze. So we have Vp equal to Zp, the impedance, okay, equal to Vp over Ip. So we have equivalent circuit over here, for example. So we see from here, I will try to break up the circuit at the primary side. So we could see that here, let's say we have our Zp, okay, Zp over here. So this is what you are currently doing. This is what we are currently doing. So we have Zp over here equal to, Zp, yes, Vp over Ip here, this one, okay. And this is actually equal to AVS over IS over A. And this is, you rearrange, you got A square VS over I over IS, okay. So we can say that, so because we know that here Vp, right? So let me focus here. So over Vs, and this is E. So rearrange, we have Vp equal to AVS, okay. So this relationship again substitute into this, okay, Vp equal AVS. So what about this one? So this is nothing. So we have actually Is over Ip equal to A. Okay. So thus Ip rearrange in terms of Ip, so you might get Ip equal to Is over A. Okay. And again, this relationship into here. Okay. So Ip equal to I over A. So next, just rearrange again, so you get that Zp is actually A square Zs over Is. And thus, yes, Zp equal to A square Z load. So since Vs over Is is Z load here, okay, here Z load is equal to Vs over I as the Ohm's law, okay. So Vs again over Is is actually Z load here. Okay. Then we can say that we can simply match the magnitude of load impedance to the source by having this relationship. Okay, Zp equal to A square by picking the proper turns ratio. You see the proper turns ratio Vs. Okay. Oh, sorry, A square Z load. Z load. Okay, here. All right. So here again to here. Now, the easiest way to analyze the circuit for each voltage and current is to replace the portion, so this is the keyword, the portion of the circuit on one side of the transformer by an equivalent circuit with the same terminal characteristics. So this is what we have done in this particular slide. So this is the equivalent circuit as well as the portion, or as well as the part of the one we have analyzed. Okay, then this process known as referring the first side of the transformer to the second side. Right. So Thevenin's equivalent circuit of transformer circuit. So this is again nothing but alright here, and also the description equivalent circuit when secondary impedance is transferred to primary side and ideal transformer eliminated. So we have seen here from here. So the basic construction over here, I can actually simply draw. So we have here and here, for example. So you have IP, okay, and then we have the VP over here. So we do have the winding that's not proper, sorry. So winding over here. So we have the ZL, okay. So this is ZL, for example. So we have IS, okay. And then we do have the VS over here. Okay, so we have the positive, negative. Similarly, here we have the positive and negative of the VP, right? Or the VAC, for example. And we can actually come up with the equivalent circuit when the secondary impedance is transferred. So we have the secondary here, all the part over here. So being transferred into primary side over here, and eliminate the transformer, the ideal transformer, the one I circle here. Okay. So how the equivalent circuit looks like after we transfer everything from load or secondary to primary. So now we have the new Z load, which is A squared Z load. So this is proven here, right? Or here. Okay. All right. So we do have a new ZP in this particular equivalent circuit. Okay. Same goes to one we have in the second figure, right? So this equivalent circuit when primary source is transferred to secondary. Now we do have here primary. Let me change the color. So let's say we pick the yellow one. So the yellow color one, here to here, and here to here. So eliminating transformer. So what will happen? So ideal transformer is being eliminated. So we do have the existing Z load, all right. Since the new element is coming from primary, now the VEP or the VAC, let's say this is VAC, is now crossing over the transformer to the load side. Okay, again, it's crossing over the transformer into the load sides. We do have the A, the turns ratio, and once it's crossed over, now the value, the original value or the existing value of VC need to be divided by A. Okay, so we have VAC over A. The rest unchanged. So we have the existing IS, VS, as well as the Z load.